Hello, and welcome to the TI Precision Lab series that looks at the decision process for choosing either a SAR or a Delta Sigma converter. This video will cover a step-by-step decision tree to help find the best converter for your application. The concepts used in this decision process were reviewed in the previous videos, so let's get started. For reference, this is the entire decision tree that we will cover in this video. As we progress, we will step through each decision and provide supporting details and examples to clarify the choice that we make. The decision tree starts with sensor-specific inputs. There are a number of Delta Sigma converters specifically designed to measure a certain type of sensor. Examples include RTDs, thermocouples, and weigh scales. These sensor-specific products normally have a wide range of integrated features that facilitate the measurement of a specific sensor. For example, an RTD solution will include precision excitation current sources. Thermocouples frequently have open sensor detection and a local temperature sensor for cold junction compensation. Typically, these types of converters are optimized for DC signals and have high resolution. In most cases, this kind of application will be measured using a Delta Sigma, but there may be some exceptions. The SAR may be used for measuring sensor outputs when a lower resolution system is sufficient and a fast scan rate is desired. This slide shows an example where multiple thermocouples are connected via a multiplexer to a discrete PGA and a SAR converter. Keep in mind that the multiplexer and PGA are a discrete front end, and the Delta Sigma option integrated these components. As mentioned previously, the Delta Sigma is more common for low frequency type sensors, but there can always be exceptions based on cost or other criteria. In the previous decision, we saw that some Delta Sigma converters include integrated features for sensor signal conditioning. However, this is not exclusive to sensor-specific products. Many useful features may be integrated that are general purpose in nature. For example, some devices include filters, voltage references, threshold detectors, programmable gain amplifiers, oscillators, and RMS and CRC calculations as well. Traditionally, Delta Sigma converters tend to include more integrated features, but lately this is becoming common in SAR converters too. The next decision to consider is whether the application requires DC accuracy but low resolution. Is a SAR or a Delta Sigma converter better for measuring low frequency signals for converters with less than or equal to 16 bits? It turns out that in this case, both types of converters have excellent options here. In this slide, we focus on the Delta Sigma option. This kind of Delta Sigma would use a low latency digital filter to minimize noise. They also will frequently include an integrated multiplexer and a PGA. Typically, this kind of converter is referred to as a general purpose Delta Sigma ADC. These devices can be found in very small packages and often will have a lower price point. This slide shows the SAR option of the general purpose converter. One advantage of the SAR converter is that it may be used to take a fast snapshot of the DC input signals and then enter a low power state. Also, there may be an application where most of the signals in the system are DC, but some signals require faster sampling rate. In this case, the SAR may be the best option. If all the inputs are DC, then you can choose either solution based on cost, package size, or other specifications. When monitoring DC signals with a high resolution requirement, the Delta Sigma converter will usually be the best solution. Remember, the Delta Sigma uses noise shaping and an internal digital filter to get very low noise. Also, some will integrate a 50 or 60 Hz rejection filter. Finally, many Delta Sigma converters integrate a high impedance PGA, so an external amplifier is not required. But let's look at a SAR option. Here we show a higher resolution SAR converter being used to monitor DC signals. Normally, a Delta Sigma would be used for this kind of application, but a SAR may be useful if one of the signals is of higher frequency, or if the system is used to take a snapshot and remain dormant between samples. SAR converters do have high resolution options, but typically the high resolution SAR is not used to monitor DC signals. Finally, for the ultimate low noise DC precision measurements, Delta Sigma converters are the best option. These devices can have resolution up to 32 bits and can have ultra low noise. The ADS1263, for example, has a total integrated noise of only 7 nanovolts RMS. Furthermore, the integrated digital filter can be configured to reject both 50 and 60 Hz noise. Some measurement applications need to take a snapshot of a transient signal at a specific time in order to capture some key event. For example, a protection relay application needs to capture a transient fault voltage in order to activate a protection circuit. In this kind of application, the SAR converter is the best choice, as the sample and hold input will capture the waveform at a precise instant in time. The delta sigma, on the other hand, averages several input samples over a time interval, which introduces latency. The diagram on this slide illustrates the snapshot action of the SAR and the averaging of the delta sigma. When higher frequency AC signals need to be measured, a wide bandwidth delta sigma converter or a SAR converter can be used. For the delta sigma option, these devices will contain a wide bandwidth flat passband filter with higher latency. Remember that latency is essentially a delay between the input signal and the digitized output signal. The delta sigma option can only be used in cases where low latency is not important. For example, a short delay may not impact an audio, seismic, or medical imaging application. In the next slide, we will do a quick review of what causes latency. High latency is mostly associated with wide bandwidth delta sigma converters. SAR converters do not have this issue because they do not contain digital filters. The problem is related to the implementation of the flat passband filter. This filter has many delay elements, and each delay element introduces one conversion cycle of latency. A typical flat passband filter can have 50 or more cycles of latency. Delta sigma converters can use the low latency sinc filter. However, this type of filter is not optimized for wide bandwidth operation due to their passband attenuation. Thus, wide bandwidth delta sigma converters will always have latency delays to consider. In applications where both wide bandwidth and low latency are required, the SAR converter is the best choice. Some examples where low latency is required include control systems, safety relays, and position sensors. Basically, any application where an immediate response is required for digitized input signals should use a SAR. That completes the decision tree for choosing between a SAR and delta sigma converter. You may find that in many cases, both types of converters are viable options. So then how do you choose? Some things to consider are overall solution size, power consumption, and ease of use. Sometimes the features in heavily integrated devices can be very helpful, but in other cases they add unneeded complexity. If you want a very simple converter without configuration registers or other features, some SAR converters may be a good option. On the other hand, sometimes the integrated features can eliminate the need for supporting peripheral components. Driver amplifiers, voltage references, and crystal oscillators add area, cost, and complexity to your system design. If these are integrated, that can be very helpful. Sometimes a performance specification, like SNR or THD, may be your key decision criteria. In some cases, the ADC may already be integrated into your microcontroller, so the converter topology is predetermined. That concludes the introduction and comparison of SAR and delta sigma converters. This slide reviews the three key options that we considered. The SAR converter is mostly used to capture transient snapshots and for AC applications where low latency is important. It can also be a good choice for small, general-purpose converters. The DC optimized delta sigma converter can have very high resolution and low noise. Frequently, this kind of converter can be used for low-frequency sensors like RTDs. Wide bandwidth delta sigma converters can be used for many of the same applications that SAR converters are used for. However, they cannot be used where low latency is required. That concludes the theory part of this video. Thank you for your time. Keep watching to try the quiz and check your understanding of this video's content. Question 1. What kind of ADC is best for measuring an RTD or thermocouple temperature sensor? A SAR, B, a DC optimized delta sigma, or C, a wide bandwidth delta sigma? The answer is B. A DC optimized delta sigma often includes useful features for sensor-specific applications. Question 2. True or false? Wide bandwidth delta sigma converters will always use a high latency filter. The answer is true. These filters offer a flat passband at the cost of added filter delay elements and higher latency. Question 3. Which of the following is true? A. SAR converters are used for low latency DC measurements. B. SAR converters integrate current sources and PGAs. C. SAR converters take a snapshot of transient signals. Or D. SAR converters use a high latency integrated digital filter. The answer is C. A SAR converter is optimized for fast, low latency measurements and typically does not include these other features. Question 4. True or false? A wide bandwidth delta sigma converter would be a good choice in cases where low latency AC measurements are required. For example, a control system. The answer is false. A wide bandwidth delta sigma would introduce too much delay, so a SAR converter is probably the best choice.